minima. Suppose assume that we have worked on this maximum, then you satisfy the Euler's equation f dash of x equal to 0. Okay, then you try to find the, you need to solve the equation. Based on that one, you try to get the information for the problem, right or not? You are trying to find the maximum minima, but what happens if you assume maximum minima exists? If whenever it is exists, you try to say that it satisfies the Euler's equation f dash of x equal to 0. That means if you know the solution for this problem, then you can get the solution for the original problem. If suppose this equation, the Euler's equation no solution, then you can say the original problem has no solution. Correct? That means when we try to find the necessary condition, it may give some information. For example, we are trying to find necessary condition, you may get some equation x equal to b form. Okay, f of x equal to y form. You try to solve that equation. It may be simple compared with the original problem. Another one, fixed point problem. Okay, next differential, maybe it is to differential equation. For example, if you study calculus of variation problem, for example, isobarimetric problem, something like that you study now, you won't solve the problem immediately. Then when you try to solve, you try to get one equation, either Lagrange's equation, where you will get some differential equation. You will try to solve that equation, then you will check whether it is a correct one or not. You will substitute, you will get the information. Understand? That means you cannot solve the original problem immediately. So derive the necessary conditions. After deriving necessary condition, you may get some simple problem. So based on that simple problem, there is a chance you may get the solution. But if there is a luck, you may get the problem is to some well-known problem. For example, solution of differential equation, solution of a fixed point problem, or solution of a variation problem. Some simple equation x equal to b, like that you can get. So use the theory. Already developed the theory in the literature. Use that theory, you may get the solution for your original problem. So that's the idea. Okay. Suppose again the problem is what happened. Suppose you are able to construct, then you try to see whether you are getting the right solution or not, the expected one you are getting or not. If you get, you are lucky. If you are not getting, that is how you are also lucky. Why I am saying that? First you are not getting means it is impossible. That is also one result. Suppose you are getting one solution, that is a unique solution you can write. Again, next one you are going to get infinitely solution. It has some nice property also. That is also good. All three also results are valid only. No result, that means existence is not possible. That is also one result. Suppose exists, again the existence is unique. That means you will get only one solution. That is also fine. After that, suppose you are going to get more solutions. Sometimes you may get the desired one also. Expected. For example, regularity may get. Okay. Understand? This is a general strategy. Do you understand or not? So now we can realize now why it is happening. Now my aim is to solve. My aim is to construct the wavelet. Okay. So now first, before already I told you in the literature, while I believe there is an example. So it is given in 1910. Okay, but the problem is started in 1980. Okay, wavelet concept is started in 1980. But before that, in literature, 1910, have given one example. So hard wavelet. So this is, so look at this function. You can say that this function I already discussed. This function is an orthonormal wavelet. Already in the lecture class, sir put all those things. It has compact support because support is 0 to 1, and here the moment is 0. Okay, 0 is equal to 0. So next the function is but the function is discontinuous at the point 0, 1 by 2 and 1. So now what happens? Because orthonormal, once we have the orthonormal, you have an orthonormal basis. You have the Fourier expansion, because f of x equal to inner product of x comma en like that. In the particular case, you are trying to use the wavelet one. So you are going to get, but here in the case of R, the function is discontinuous. So it has issue. But what happened? I already told R constructed, but these functions are discontinuous. R proved that if you take any continuous function, it can be approximated by the translation and modulation of this function side. But the main issue is function is continuous, but this function is discontinuous. Approximation function is discontinuous, but original function is continuous. Most of the time, we will try to expect that it should come from the same. For example, continuous means we expect that the approximation function also continuous. We expect, but it won't happen. So this is the first problem with the R-wavelet. But that time, no one discussed why we need all those. People did not discuss that. Okay, because 1910, after that 1985 something, 1980 something. Okay, so this is the first one. Okay, fine. So now we have one more example. Now we are trying to find the function phi as a discontinuous function, but the aim is to find function phi which has which is sufficiently smooth. There is some addition. For example, phi may be differentiable or infinitely differentiable, like that we can expect. Okay, so now what happened? Even though we have seen example with the expected one, we are not getting. So we will try to. Is there any possibility to construct other wavelet or not? So now I already told that. Suppose we know if you assume it is a wavelet. Suppose if you assume it is a wavelet, then what happens? Let psi be an orthonormal wavelet. So here define Wj equal to square of this one and Vj equal to this one. Then what happens? So then the function that Vj should satisfy all these properties. Scaling property, external first, scaling property, trivial intersection and density. Finally, orthogonal decomposition. Vj plus 1 equal to Vj plus W. Now what happened? So I am not getting, suppose what happened, I am not getting any information still. But what happens? Okay, so these are the necessary conditions. Okay, so any additional necessary condition? Yeah. What happened? So we have already one exam is there, hard wavelet exam is there. So you try to analyze that one. It may give some information. Sometimes general theory is not giving information, but you try to understand the theory behind the hard wavelet. So it may give some information. So what happened? So now from the hard wavelet example, you can realize that this V0 is simply exotic span of 1k and V1 is just to follow the nested property. Okay, so you are going to get that one. So that is what happened. So here there is no information on some function phi because there is no information. But when you are trying to analyze the hard wavelet, you want that space is generated by one single function phi, new function. Okay, not same side. New function. Not saying that. I am not telling that this is the same as hard wavelet. This is different function. Okay, this is 0 to 1. That is 1 to 0 to 1 by 2 is 1 minus 1 by 2 1 is 0. Okay, this local is 1. So it is generated by this one, and further it forms an orthonormal basis for this one. So now the idea is, suppose you can expect that, okay, instead of taking this function, if you choose some different function, there is a chance. There is a chance you may get the information. Okay, just assume it. Okay, go further. I am saying that, okay, no problem. Just go further. What's going on? So try to get the information. It may help you. Okay, fine. So now I am going to assume that one. So okay, this is the one. So now what happened? So here am I. Okay, I will try to choose that one. So suppose I have a sequence of closed surfaces satisfying this property. Additionally, I am trying to choose this is forms here. Or these bases I am taking for time being, just assume this is an orthonormal basis because I don't want to discuss orthonormal these bases. Simply orthonormal basis is taken. Why here we are taking these bases? Actually, if you know the these bases using mere orthonormalization process, you can get the orthonormal basis also. So I already told that suppose if we have a basis is always linearly independent set. Using Gram-Smith process, we can always get orthonormal basis. Do you agree or not? Suppose if we have basis using Gram-Smith process, we can always construct an orthonormal basis. Okay? But now the problem is what happens when you are trying to find the orthonormal basis using Gram-Smith. There are so many issues. What are the issues? Suppose you know that 1x square this correction if you take this forms a linearly independent set based on Gram-Smith process. You may construct a orthonormal basis for certain Hilbert space. For example, L2 of minus 1, 1, L2 of 0, 1 or something like that. For example, if you choose different way, you will get different type of orthonormal basis. It actually leads to some legendary polynomial spaces, polynomial space, legendary function, Bessel function leads. Okay, some special function will go. But the main problem is to look at the original collection 1x square. It is simple monomial. But after doing Gram-Smith process, it won't preserve the polynomial property. You will get something different. Okay, suppose we understand or not? Suppose if you apply the Gram-Smith process, you may get the solution. But what happens? You may not get the simple one. It may be more complicated. That means you may not expect the same property of other orthonormal case. For example, original one is monomial, but new constructed orthonormal is not monomial. It's something new. So you may not get that. But here, in this case, if you apply the Gram-Smith process, I will get the orthonormal basis. But again, I cannot get that it is that the new orthonormal basis cannot be generated by one single element. But if you use mere orthogonal process, you will always get one function, another function size such that psi of x minus k forms a orthonormal basis for V naught. That means given a these basis, I can always construct an orthonormal basis. The same structure using Mayer orthogonalization process. I am not going to discuss that one. Okay, just about my aim is to discuss cascade algorithm. Okay, so now we'll go to that one. So now, so first one. Okay, now we are assuming suppose there exists a function. So here look at this one. Actually, these are all many things, but here based on this function phi, you can decide this all this property also. Suppose if I decide the function phi, this function automatically this property I can decide automatically. That's the next result. Somewhere that means why I am saying that you don't need to worry about other property. It is based on the existence of the new function phi. Suppose I want to construct the wavelet psi, I need to know the function phi. Okay, that's the thing. So that means what I am saying that if I am able to if I assume this phi is a real basis and continuous these things, and there exists a sequence such that phi of x equal to summation a n phi of 3x minus n equal to this one, then this collection Bj forms a MRA phi L2 of phi. So now we can realize what happened now. We want to find the MRA. I need to if I know the function phi satisfies this property, then I can find the MRA. That means the problem is construct the function phi satisfying this property. That means what you are going to get. That means this is okay. These all are very difficult problems. So look at this one. Verifying continuous. Suppose if you know the function phi, you may verify continuous or not. Because always continuous you can say whenever phi belongs to L1 of R because using Fourier transform property. And this one also you can say this normalization technique. Phi means just integral minus integral. That one also okay. Second one is nothing, but third one, first one. So look at the third one. That means if you want to construct the MRA, you should know this equation. So you need to find the function by satisfying this equation. This is called refinement equation. In literature, it is called scaling equation, two-scale relation, something you will get. But I prefer refinement equation. Why I am using refinement equation? I will tell you later. Why I am using the terminology refinement equation. I will tell you why we are calling this a refinement equation. I always prefer this one. I won't prefer scaling equation. Okay? This is also called scaling equation, but I will prefer refinement equation. I will tell you what is the reason behind that one. Okay? Fine. So now the problem is, if you want to construct the MRA, first I should know this one. Okay? So next. So now what happens? Suppose phi is a scaling function of an MRA. So now what happens? Suppose we are now I am trying to relate that one. Since phi belongs to V naught, because that relation V naught subset of V1 like that, so obviously this property should be there. That's why we are taking that one as a condition. We understand that theorem because that's a necessary condition. That's why I am not taking immediately this one. So remember that because V naught subset of V1, if I need to get it should satisfy the refinement equation. Then only I can get it. Understood? That's why in the last lesson I am taking refinement equation as a necessary one hypothesis. Okay. So now just apply the Fourier transform. Just phi root of psi equal to use the property m naught of psi by 2, like that you will get it. So this is called scaling filter. So here I am using the word filter. So if you are suppose you are working in engineering terminology, you are familiar with the Gaussian filter, noise filter, white noise filter, all those things you will get it. So in maths, just if you are a math student, filter means nothing but just squaring a periodic function. L2 function belongs to L2 0, okay, math filter. But filter, if you want to, if you are working in transform, if you are a functional analysis people, special functional analysis, filter means it is a linear transformation with additionally it should be a time invariant property. That is a time invariant property. Okay, these are the main thing. Okay, suppose you are going to filter. If you are going to if you are from signal analysis, then filter means you know what it is. Filter transforms same meaning, but again it's a time invariant. Okay, so whatever everything is related, actually all are related. That terminology is only different. Mathematically it denotes simply one operator. Okay, so suppose you are going to take the symbol is Gaussian function. Now here the Gaussian function is not meaningful. Gaussian function is called Gaussian filter. Okay, suppose if you take a linear transformation, it is time invariant. You can always relate it to one function. Then the function is called symbol or filter or another one. Some I didn't remember the terminology. Filter, symbol, one more table again to remember it. So same, just don't worry about this one. Filter here, that's just the symbol of the scaling function is there. Okay, fine. So next, again what happens? Again, if psi belongs to B1, if we take, then the last property, either Bj plus 1 equal to Bj plus that. Using that property, you can see that psi belongs to B1. That property you take. So now I am not just assuming what's going on. I am not getting the solution. Go further. Finally, we are going to get content. It is not possible. You can say. Okay, if you are going to get some information, then you can get it. So now, since psi belongs to B1, so again which is span B1 is nothing but stand by this one, just definition if you apply. Then I get that psi of t equal to this one, summation Bs. Again apply the Fourier transform. Okay, now psi root of psi equal to m1 of psi by 2 phi root of psi by 2. Okay, fine. So now here also this is called wavelet filter because it is related with the function psi. Psi is a wavelet. Suppose psi is a wavelet, if we take that psi belongs. Okay. Fine. So here also I am taking just this one. So now what happened here? So here scaling filter also there, another filter also there. So now somehow we need to connect phi and psi. There is a connection is there. So what is the connection? So you need to see. So what happened? The next one is suppose phi is a scaling function of the MRA with in this one. Then the function the wavelet filter and scaling filter satisfy this property. So the meaning of this looks like complicated you are thinking, but it's not complicated. It is telling that the matrix is simply a unitary. Just unitary transformation means you know na you are going to get this one. Correct? Just I am writing explicitly that this unitary means what at A m star m equal to int. Okay. Now just take m star 1 0 1 0 0 1 you get that equation just to equate everything. You will get exactly this things. Just equate it. Actually, m star m is identity. That is unitary matrix. M star m is identity. Just matrix multiplication you will get exactly this equation. This look like complicated, but it's not complicated. So you are getting. So now what happens? So now if you know phi of psi, if you know the function phi, can you construct the function psi or not? So the connection is here. So based on this connection, there is a whether you can get it or not. Yeah. Suppose what happened? I suppose this m0 is related to the scaling filter, that is scaling function. This m1 is related to wavelet filter, the wavelet function. So now suppose if I know m0, the scaling function if I know m1, I can get this wavelet because that is wavelet is nothing but based on the coefficient of m1. So you will get it. So now how to find this m? Suppose if I know this one, this m1, can you find it or not? Yeah, it is a simple problem. Now it is a very simple problem. That means suppose you have matrix 2 by 2 matrix. Okay, we are assuming that it is unitary. Suppose A, B, C, D. A and B are known. First row is known. C and D is what? C and D should be in this form only. The first one, suppose you are writing second one already. First one should be in this form only because there is a property of unitary matrix. Right? Suppose suppose if you have matrix A, B, C, D. Suppose if you have matrix A, B, C, D. It is unitary if you take. If you know A and B, the C and D is nothing but A comma B, that C comma D must be equal to some number alpha. A comma B, this alpha belongs to the such B for I theta. So that's why I am writing A alpha of psi. Another one here I am writing here. Also alpha psi equal to 1. Okay, the non-trivial condition. Understand? This is simple problem. Just see, look at this one. I have started something. I am getting one by one. Okay. Now what happens? Still I cannot complete. That means I am able to find the scaling function phi. Using this formula, I may get a solution. I may get the function wavelet function phi. Get that? Is it clear? That means now you can do it. That means if you want to construct the wavelet, I won't construct the wavelet phi immediately. I will construct the function scaling function phi only. I am able to construct the function scaling function phi. Then I can find I can find the original wavelet also. How to do that one? That means here look at this one. Using the property, you are going to get all the information about m1. Once in m1 you will get. So that means you need to find the function. That m1 should be in this form. This time we can do this. So after this one, psi root of psi equal to m1 of psi, phi root of psi by 2. This one the same formula you are going to get. Just substituting the original equation. Okay. After that one, so there are so many alphas I will get. In fact, many one for scaling function, so many scaling function, so many level you can construct. But it's like some modifications, translation like that only here. So just for particular I am choosing alpha say equal e1 minus I say just m1 of say I am computing everything I am getting computing. That means this is the finally answer. Understand? That means I am able to know phi, I can find psi using this. So this a1 also related to that m1 only, right? That means if I know the refinement equation with the solution a or the refinement constants, that means a not a1 like that, I can get the solution. Understand? Now where we are now? That means if you want to consider the wavelet, what you need to do? You need to solve the equation. That's phi of x equal to that one. How to solve that one? So that's the first problem. Understood or not? It is that means solving constructing wavelet is reducing to solving the another equation by the refinement equation. Correct? Understand? And now you can realize I started something. Now the general principle working here neatly. Right? And that means I have started. I try to find the necessary condition one by one. Somewhere I am getting the information. So okay. So if I try to solve this problem, there is a chance to get the solution for the original problem. Understand? Is it clear? How I am developing? I am not saying I can't get immediate solution. Just I am doing one by one. Okay. Do this one. What's going on? What's going on? Okay. This is a very important thing. Research. What happened? Most of the time I will try to inform the students what happened. Okay. Suppose someone is trying to. Suppose I am giving a definition. Everyone going to do. Suppose I am giving one definition. I am asking one problem based on the definition. Everyone is going to get a solution immediately. It's not a research problem. Just you are trying to use simple logic, then you are going to get. But in research level, most of the time, what happens, you need to work continuously. So, for example, you need to get means at least now I am writing. Maybe it will take 1 month. Okay, to complete all the things. Okay, just do it one by one. At certain stage, you may get information, good information. If you are getting good, you are very lucky, I can say. But you need to do when you are doing research. Okay, fine. So now I am getting this one. Still we are not completing the problem. We are trying to convert the original problem to another problem. Okay, that will solve the refinement equation. Okay, so now here this is a cascade. Okay, cascade. Why it is called cascade? I am trying to see. So now look at this equation. Suppose for simplicity, I am assuming that the function is combined. I just condition I add it. No need to worry. Okay, you are going to get contradiction. You are not going to get some nonsense information. Then it is never possible. That's all. Okay, that is also result. Okay, fine. So now I am writing compactly supported function. So that time I am getting simple equation. So what type of equation it is? So it is a functional equation. Okay. It is a functional equation. That means one side by the other side, that means you can solve the equation. For example, look at the differential equation. You will get more information on differential equation. That means everything based on the function by one equation, the translation and direction. So that means whatever this equation will get. So now I will solve this problem. How to solve this problem? Now actually I am getting the fixed point problem. Look at this one. I am going to get I am not consider how I am writing. That's a functional equation. Okay? Functional equation is what? What happens? You know the fixed point problem. What is the fixed point problem? Suppose f is a function from x to x. If you want to say x is a fixed point of the function here, you need to say that f of x equal to x. Correct? Correct or not? This is the one. Suppose you want to say fixed point, this one you are trying to say. Suppose how to find the fixed point? Suppose if I know xn converts to x some sense. Xn converts to x. Okay? And f is a continuous function, then what you are going to get? You will get the solution. F of x, that means limit argument you take it, you will get f of x equal to f of x. So now look at here. So here phi is here I am taking x is L2 of r. I am taking x equal to L2 of r. I am taking. Okay, I am trying to rewrite that equation. How I am writing? Right? Just I am writing f is a function from L2 of r to L2 of r by f of phi equal to summation a n phi of 2 dot, okay, for that 2 dot minus n because function f of phi. That means now look at this. I am trying to say that suppose this function has fixed point. Then what's the meaning of this one? It is f of phi equal to phi. Then you get an equation only. So now we are going to get the solution. That means I am getting functional equation. So after solve this one, use the fixed point idea. Understood or not? Is it clear? That means now what I am getting. So now I am able to convert into some well-known problem in maths, fixed point problem. So fixed point problem. So now what happened here? Once if you know fixed point problem, one of the important fixed point theorem is Banach fixed point theorem, Banach attraction principle. But here we don't need that one. You can attempt. Okay, I am saying. Suppose okay, fixed point theorem. Can you apply the Banach fixed point principle somehow or not? Okay, you can attempt it. Yeah, we can try. But for this case, you don't need Banach fixed point theorem. Always it will work. Okay, but this time Fourier transform technique. So now you can realize. That's why you can realize that. Suppose under certain assumption on a scaling filter, this one here, under certain assumption on scaling filter, okay, the conditions you need, I will try to explain. Suppose phi of x is converged to phi j of x, where phi naught of x is equal. I am taking the b spline, linear spline, n2 of x is this function, n2 of x is simply, that means initial condition, okay, Banach fixed point theorem, that means phi naught equal to then f of phi you are going to get it. So I am going to get phi naught of x equal to just n2 of x. So this is the idea. Suddenly here also I am missing something. Why I am choosing n2 of x? There is a information. Okay, I am missing, but I try to because already there are many relation. This type of relation is available for b sprites. Okay, in approximation theory. So due to that reason, they are trying to decide that one based on certain reason. Okay, understand? Is it clear? So I am getting this one. Now what happens? Once this is done, then you can say that phi of x converges to phi j. That means phi j of x and defining. Then using that one, I am going to get phi of x. Understand? That now that's why I am using the refinement equation. Why it is called that means if you want to find phi of x, first you take phi naught of x. Next again refine the equation. It means phi 1 of x based on this one. Again refine the equation, you get phi 2. Again you do it, you are going to get phi of x. So that's why it is called refinement equation. Understand or not? So why I am not referring scaling equation? Is it clear? Fine. So refinement equation calculation. Okay. So now what happened? By simple computation was support, that means this function is the n is supported from 0 to 2. Okay, n is supported, that n2 is supported from 0 to 2. Support of I naught is 0, 2. So using that previous equation, just to look at this support just because of translation, you will get it, and due to this 2, you will get from the other some factor. So due to that, this 2 is coming 15. So just a simple calculation, nothing. Okay, not difficult calculation. Just because of shifting and because of dilating. So you are getting the 2 plus x was because of shifting and dilating 1 by 2. So that's why you are getting this one 0 plus 2 plus n. Okay, now what happens? So now follow this one. Now what happens? If you follow this one, now you support of, I think here I mixed it 2 power j, 2 power j, 2 power j. This type of support of here, phi j equal 2 plus 2 power j minus j, 2 power n infinity. Now as n tends to infinity, this quantity goes to exactly equal here. Just give the property. 1 by 2 n converts to 0. Okay, 1 by 2, 1 minus 1 by 2 n. First one is 1 minus 1 is 0. 2 is 2 plus 2. This circle you get, there's nothing else. So support of phi is you are getting the limits. If it exists, what happens? Now you can realize still they are not completing. Okay, that means phi naught. Suppose you are this one. Main problem is we should know what is area. Then only that you should know area. That is also next problem. That leads to finding area. Okay. So now you can realize. So now this is the reason. Now due to this reason only I think cascade. Because cascade means what? The first input, the first output will be an input of the second machine. Okay, for example, phi naught, you are giving phi naught, phi 1 is giving. Next, you are going to give the phi 1 as the input in the second machine. So that's why this iteration is given. So that's why it is called cascade. Okay, cascade means what? One by one. Okay, so that's why it is called cascade. Is it clear? Fine. So now what happened? So this one I am getting. So next, so there is an advantage. So there is a suppose what happens. Still I am not able to I am not able to find the phi. But it is giving many information. What happened? So first one, when you are assuming support of phi, assuming the support of phi is 0, n, phi of k is 0 for all k less than or equal to 0 and k greater than or equal to 0. support you are 0 t and this one you are going to get, correct? So now what happened? Suppose if you know the value here I am writing later because I am answering just how I am doing, just try to understand. So if the values of phi of 1, phi of n minus are known, then the relation what you are getting phi of k, that using the refinement equation you are going to get the value of phi at the dyadic numbers k by 2j. Phi was phi k by 2, next go. That means what you are getting? That means if you know this, only if you know these quantities, you can get all the function value phi at the in these dyadic points k by 2j. So what is the advantage of this one? Anyone? So suppose I hope that if you are using wavelet, suppose I am asking the graph of Laplace's wavelet function of order 3 or like that. So maybe if you are using MATLAB, you use the MATLAB tool, then you will get it. How the code is written? Anyone? Anyone? Suppose that one I am saying Laplace's scaling function of order 3. Suppose something like that will come. Okay, graph like that will come. Okay, I am not writing something like that will come. Graph like that will come. Okay, so anyone, how the graph is computed? Anyone? This is the algorithm. So what happened? So what you know? So using this form, suppose once if you know phi of 1, phi of n minus 1, using this, if you know the values, I can find all the values of the dyadic rational numbers. So remember the dyadic rational numbers are dense in R. They are not. Dyadic rational numbers are dense in R. That means what happened? Once I know this one, based on the I will try to find based on first I will try to find. So 0 to k I will fix it, all the numbers 0. The first one condition. So next I will try to find suppose phi of 1. I know if I know phi of 1, phi of 2, suppose phi of 1, this one is I know, then I will try to find. Next what happened? I will try to find phi of 1 by 2, 1 by 4, then based on the equation I will try to find. Every time I will try to refine, then I will try to get all the information because dense is there na. All the rest numbers are dense. So you are going to get the graph. Understand or not? So now that's why Laplace is very powerful one. Okay, suppose I am giving existence. After that, you are not able to draw the graph. Sometimes you may not get a good information because when you are doing computational work, you should know the graph. Sometimes explicitly will always help you. Correct? Fine. So now that's what I am saying. Now we understand or not? So now you can get it. So now what are the bending things? Now up to this one, this is bending. So I am assuming what are the assumptions? Under certain assumptions of the scaling function, this is the bending. Okay, that means what is the value, how to choose the value of a. Okay, that is the bending case. If I assume that one, I am bending. After that, if I assume these quantities, I am able to get other values, other random numbers. Now, how to find this phi of 1, phi of 2, and minus 1? Okay, I am trying to solve one by one. Okay, fine. So now what happened? So determine the value of phi of k belongs to. So what happened? Use the refinement equation. With x being integer, then just substitute one system of equations only. System of linear equations you are going to get. Okay, just substitute. Give integer quantity or system of equation get, then you can solve the system, you get the value. That means you are going to get b equal to a form, where b equal to this one, and sorry, get a equal to a to g. There is some typo, not m, this is a. Okay, so okay, then already I used one m, that not that m. So here this a. Okay, so you are getting this equation. Now solve. That is what happened. To find this one, you try to solve this problem. That means what is the eigenvalue problem? Simple eigenvalue problem. Do you agree or not? So try to find it. That means, so using this one, you try to and one more thing. Most of the time, this function satisfies some additional properties. For example, the function phi should satisfy partitionability, all those things. You can get that. Okay. Is it clear? How it is going? Do you understand? I'm just I started the problem conception. I want to construct how I am going. Just to try to find the necessary conditions. Not only there are other necessary conditions also there. I am not going to discuss that one. Based on Fourier transform also necessary conditions. I am not discussing that one. Okay. So now here in this table I am going to get so many information. So this is helping or not? I am trying to see. Okay. Fine. So now what happened? I am giving one example. So now this one. Suppose if I am taking one function. Here main problem is remember that This 1 plus root 3, 3 plus root 3, these numbers are still you don't know how to find. That because I have to know under certain condition on the scaling filter I have to know. So that one how to choose that one. Okay, that is also I did not discuss. Suppose assume that fact. For example, I am taking the average scaling function. These numbers are not it is not computed. It is not taken by trial. There is a way to find. Okay, there is a way to find. Okay, I am not going to discuss this one. Okay, fine. So just for the time being, just to take this one. Okay, I am getting this one. Now this case n equal to 3. That means support is 0 to 3. The function support is 0 to 3. Now what happened? Suppose what happened? I want to know I want to draw the graph of this function. Because it is not written in explicit form, not in a concrete form. Then phi of x equal to e power x, phi of x equal to sin square x are any linear combinations of elementary functions. Okay, but the function is given in this form. Then how to draw the graph? Okay, now what happened? I will try to find first the matrix A. I am trying to find that A1, A0, and matrix whatever I have written. Because in this case I will get 2 by 2 matrix. Because n minus 1 I am taking now. This one. This matrix. This matrix. And equal to 2 by 2 matrix, then A0 everything get it. So now solve the equation. So actually the solution is this one. Okay. But again using the one more normalization condition. In this condition if you use, you can decide the value of so the system of the equation and just solving. And not because you will get so many solutions because it is you are trying to find the solution. You are trying to find the eigenvectors of the one eigenspace. Remember the eigenspace is not you won't get every single set. Okay, that's why you are getting so many numbers. So this A will decide which one based on the additional condition. We are getting A equal to that. Now let's get the phi of 1 plus phi of 1. So A equal to 100. Understand? Is it clear? So that means once A equal to 1 by 2, now phi of 1 I am able to find. Let's solve it now. 1 phi of 1, phi of 5. So now what happens? Phi of 1. That means how I am going to draw this graph. First I will try to draw phi of 1, 0, 2, 0. I think 0, 0, 3. 1, 2. I will find it. Now I will try to find the scaling function based on that cascade result. So 1 by 1, that's 1 by 2, 1 by 2, I think 1 by 4, like that I try to get something like that. So graph. Understand and say, is it clear or not? So I am not saying the function is not given in the concrete form. Okay, it is given in a functional equation, but still I am able to draw the graph. Is it surprising or not? Sometimes suppose I give phi of x equal to e power x, we will try to draw the graph. Suppose other for sin x or linear combination, then you will try to draw the graph. There is no issue. But this function is not given explicitly. But still I am able to find the graph. Why? Due to this one, cascade. So that's why it is not only existence, the graph is given explicitly. That's why we are using now I can say that law basis functions also elementary functions. Okay, not only LIAT, logarithmic, inverse, other one. Okay, these functions also elementary functions. Because it's not number, I am able to draw. Because e power x is also not elementary function concept because it is written in terms of infinite series form. Okay, understand? So that's why it is called. That's why it is a powerful tool, law basis scaling one. Okay, but still I am not focusing what happened. There is an issue how to find this coefficient 1 plus root 3, 3 plus root 3 by 4. So this problem, that's the next one. I am not going to discuss. Okay, is it clear? Cascade algorithm clear? So now you should know how to draw the. Suppose in the books, this graph is given. How they suppose if you see the averages, 10 lectures on the graph is given everything. How the code is how the graph is computed, drawn. Okay, based on this cascade. Is it clear? Next slide. Okay, so my next topic is sampling theory in 15 variant space. Actually, look at this one when I'm trying to construct the spaces.
So, can you differentiate between basis, ridge basis, and frames?
Okay. Basis means first algebraic basis or Hammer basis. Next one is Schauer basis. Next one is basis. Next to frame.
With any simple.
Okay. I will give you an example. So Hammer basis means it is a collection of vectors. It should be linearly independent. And if you take any element belongs to the space V, it can be written as finite linear combination from the given finite linear combination. Okay, because in the vector space structure there is no meaning of infinite sum. Okay, understand? Hammer basis or algebraic basis. Next, suppose it is a Banach space or non-linear spaces, we can talk about the convergence. Schauer basis means what happens? You will always try to take countable sequence of vectors. Okay, the countable sequence of vectors is called Schauer basis. It should be a linearly independent. Further, it can be, if you take any element belongs to the vector space, it can be written as infinitely linear combination AN form. Further, the ANs are unique, and the equality based on the distance on the metric space, the vector space, okay, non-linear space. Okay. So next, Rees basis is nothing but the generalization of orthonormal basis. Okay, generalization of orthonormal basis. Okay, orthonormal basis we can say this is generalization of orthonormal basis. Okay, that time what happened? Instead of finding instead of finding orthonormal basis, Rees basis should be an image of an orthonormal basis under bounded inversion of it. Okay, this is the connection. And plane is the more generalization of basis under. Very simply satisfy the plane inequality. That one. Okay, this is the one. Rees basis, orthonormal basis implies Rees basis. Rees basis implies plane, but the converse need not be.
Yes, we can say that the frame contains all truths.
Which one?
Frame is the
Big, yeah, frame is the biggest connection because
it
frame
contains
is
basis and Rees.
yeah, actually every Rees basis is a frame.
And what is the relation between Rees and basis? Rees basis and basis.
Rees basis actually basis is simply algebraic basis means there is no relation.
But the containment which contains which asking.
Schauer Rees basis implies Schauer basis, but converse is not. Okay. So next, sampling theory. So now here I have discussed MRA. At that time what happened? We have chosen one space V naught of phi. V naught equal to span of one collection phi of x minus k like that. Correct? That usually that space is called shifting invariant space because we are shifting by integer. It's called shifting invariant space. Okay. So and one more thing, whenever you are trying to talk about wavelet concept, actually you try to choose the wavelet to satisfy the interpreting property. Sometimes you should know whether the wavelet function or the scaling function satisfy the interpreting property. It's a crucial one. Okay. Some meaningful you should know what is the interpreting property. Because why we need? Because when I try to write the orthonormal series based on wavelets, that you should know what is the value of the inner product, psi j k or psi m. How to find that? Is it possible? Because finding them is not easy. So what cases that quantity you can say immediately? Suppose the psi satisfies the interpreting concept or the sampling condition, you can say that that quantity is exactly equal to a function at certain point. Function value at certain point. Okay, so that's the main advantage. Okay, so now I'm going to focus on some important problem in this area. Okay, so first non-orthogonal Fourier series. Okay, there are some important research problems in this area. So computational harmonic analysis is really one. First one, Fourier analysis. So Fourier analysis, you are not familiar with the Fourier series and Fourier transform all those things. So what is Fourier? Suppose if you take your interval is 0, 1. Suppose I am taking interval is 0, 1. Okay, so one of the Fourier conjecture. Okay, one of the important problem. Suppose I am taking my interval is 0, 1. I know that e power 2 pi I nx forms an orthonormal basis for the space L2 of 0, 1. Or you can take another one, e power pi I nx by square root of 2 pi. It forms an orthonormal basis for L2 of minus pi, 5. Do you agree or not? Okay, just I try to explain the problems. Okay, if you are interested, start. These are very difficult problems, not easy problems. Okay. So what happened? Suppose I am taking this e power 2 pi I n x. It forms an orthonormal basis for this n belongs to z. Forms an orthonormal basis for L2 of 0, comma 1. Okay, fine. So I am writing this simple problem. Okay, but it is not easy to solve. Okay, that's the one. Okay, fine. Simple problem, but it's not easy to solve. Okay, that's why it's conjecture actually. So e power 2 pi Lx this one I take. Suppose here instead of 0, comma 1, because what happens many times authors will try to take minus 5, comma 5. Suppose L2 of minus 5, comma 5 they try to take. So that time what happens? So you are going to take e power 2 pi x, sorry, e power pi I or I n x by square root of 2 pi. Maybe here some factor will come, some constant. N belongs to z. It forms an orthonormal basis. Do you agree or not? Just small, just change the variable then you get the solution. Correct or not? E power 2 pi n x or e power, because when you are trying to integrate, just apply the change of variable, it will be adjusted. Only thing is you should know the value of integral 0 to minus pi to pi e power I n x is simply delta n 0 something, that one. So use the fact, then you will get that one. Based on that one, you are trying to normalize the numbers, correct? In general, suppose I am taking some interval L2 of a comma b. Okay, so e power 2 pi I n x by b minus a 1 by square root of b minus a, n belongs to z, function orthonormal basis for 4. Okay, do you understand? This is just simple dilation only. Just trying to apply the change of variable, they are adjusted. So they will not affect anything. Okay. Because some other they try to follow minus pi to pi, some other they try 0 to 1, some take 0 to 2 pi. But there is same. The computation they are trying, right? You need to modify accordingly. That's all. Nothing else. Okay. This is a problem. So now next problem. So instead of interval, I am going to take union of two intervals. I am going to take union of two intervals. Suppose L2 of a comma b, I am taking omega equal to a comma b union c comma d. These are disjoint. Okay, because the result is not disjoint, again it comes to interval. So always try to choose it is disjoint. A comma b and c comma d. So now can we find the similar type of basis for the space L2 of 0 by 2 of omega, where omega equal to the union of two intervals, disjoint intervals. Can you find it? Yeah, sometimes what happens, mostly there is a story about this problem. People always they will ask, okay, just apply the change of, so suppose just apply the change of variable and modify this one, you may get it, you can say. Okay, what happened? You will get one simple example. Suppose I am taking 0, 1 and 2, 3 if I take, I will get the solution. I can construct it. I am trying to choose correct 0, 1 and 2, 3 I am taking. If I take this one, I can always construct an orthonormal basis for this basis in this form, equal to 2 pi lambda, but lambda is not necessarily here, some different set. Okay, understand? Just after change of variable, adjust I will get it. Okay, by using that change of variable. Suppose I am taking some, I am taking 0, 1 and 2, 3, I can get it. I got the change of variable technique. Suppose I am taking 0, 1 and 1.5, 2.5 I am getting. So can you find it? The same trick we try to do, it won't work. Okay, that means what's the problem? So the problem is construct the exponential orthonormal basis, that is this form. In general, this basis, okay, exponential orthonormal basis of this form for L2 of omega. The conjecture is, what is the conjecture? If you want to say if the existence, that means exponential orthonormal basis exists if and only this lambda times omega. That means what is the meaning of this one? For example, if you take the condition is a Fourier conjecture. So people are trying. Suppose I am taking conjecture is lambda plus n should be equal to something I am not writing. right here. Okay, these are conjecture. Suppose the conjecture tells that if you want to say e per 2 pi lambda is a orthonormal is an exponential replacement, first this one you should omega and lambda should satisfy this problem. Okay, this is a conjecture, just a conjecture. Okay, the conjecture is this. Higher dimensional up to 4 proved by Darmstadt is disproved by Darmstadt proved that Darmstadt and other people proved that the conjecture is not true for higher dimensional case, especially for 4, 5, 6 like that. I think 2 it is 2 and 1 it is open. Okay, I'm writing only for one dimensional case, the problem is open. So why this is important? This problem actually, the problem is related to signal processing. It is very important because what happened, the construction of this problem is construction of the basis equal to finding certain orthonormal sampling set in multi-band interface. The problem is simply I'm writing math problem, but the problem is in signal analysis finding the sampling set for a multi-band interfaces. Okay, so for then you try to use the technique sometimes signal analysis concept to solve the problem also. That means sometimes the original problem will not get the solution, but after converting by experiment, you may get some solution from the other equation. Okay, so next to problem is Ramesh closing problem. So it tells that so try to find the value of a and b for a given function phi. That this function forms a frame for network. It is called Ramesh's closing problem. So it is in Gavron is the time frequency analysis. We discussed what is Gavron time frequency analysis. One problem. So next problem is most of the time forward sampling problems are rigorous pure and applied math. Sometimes what happens, this is a purely applied math problem, but you try to see the theory behind mathematical theory behind that theory. What happens? Suppose you are someone, for example, I have done many work in this one because I have math background. I don't have any knowledge from C. But what happened? Whenever studying, I will try to see some problem. What is it? Sometimes with engineering people, they won't see the mathematics because sometimes they try to write simply why it is working. So they will try to say. They won't say what is the reason behind that one. So what is the mathematics behind it? Sometimes that one I will try to focus. So here I am focusing this problem also. Finally, applications in signal processing. For example, so these problems are, you may feel something different, all are related. For instance, these conditions. Actually, these conditions, suppose we are working in numerical analysis. One of the problems is one area is finite element methods. Finite element methods this is playing a crucial role. Standard condition. That means standard condition is that suppose if we have a approximation problem. Suppose you are trying to find the numerical integration of certain function. So what happens is suppose you try to find the approximation based on Lagrange's interpolation, then you try to find the solution. Now the next question: for what cases you will try to get zero error? For what function you get zero? For example, suppose you are trying to find the numerical integration based on trapezoidal rule. So you know that you will get always zero error. The function is the linear function. Right or not? You will get it. So that zero function. That means always linear function you will get it. So now what happens? Most of the time what happens? Standard conditions tells that suppose if the function higher order polynomial if you get, then smoothness will be increased, that error also will be reduced. That will be increased standard. Okay, fine. So I am here prediction problem. So what happens? Prediction problem is I will expect perfect recursion. Sometimes what happens? Most of the time perfect recursion means there are two things: exact recursion and perfect recursion. Perfect recursion for me avoid truncation error. Most of the time what happens? You will try to get the formula based on infinite sum. Okay, you try to get infinite sum. How to avoid the infinite sum? Always try to need to get the finite sum. This is possible. So that is the perfect recursion. This is possible. Yeah, it is possible. Okay. So these are the main problem in this area. Okay, I am working actually. Okay, these are very difficult problems. The first two are very difficult problems. Okay, there are so many conjectures. It is aware you can see. Okay. So next, so now I'll try to explain what is sampling problem. Just quickly that. Okay, fine. So what is sampling problem? Just actually sampling problem is just try to reconstruct a function from sample value. So you can realize that the problem is ill posed because you know that there are many functions satisfying the same sample values. Because just suppose we have a sample value, we try to draw many functions passing through the point. It is possible or not? So that's why the problem is impossible. Do you agree or not? Impossible means it has no solution sometimes. Okay? Because if I have suppose if I am taking certain sample points f of x1, f of x2, f of x3 something, I want to find the function here. When we find here, the immediately can say it is not possible immediately because I know that I can draw many graphs passing through the sample points. It is not possible. Okay, now you need to restrict certain conditions on the function, then only you can get the solution. Correct? Unique solution. Okay, so that's why what happened. So now, suppose you try to reference given a class of function b, find condition on the sampling set x under which the function f belongs to certain class should be reconstructed uniquely and stably from the sample value. And once sometimes what is practically we should check once we run, we try to find the new efficient algorithm, numerical algorithm we need to find. Okay, fine. So these are the main problem. So here I am focusing on just find f of omega j like that I am writing. So not only this one is a classical sampling problem, there are some other sampling problems. For example, instead of taking f of omega j, we try to take derivative sampling also. That is also possible. F of omega j, f prime of omega j like that. Suppose the function or its derivative also, function values are certain its derivative also. That is the derivative sampling. I am focusing that one also. So another problem is average sampling because practically you may not get the exact location. Let's try to find the local average. Okay, local average sampling. There are many different type of sampling problems. Okay. So now I will try to. This is the classical sampling problem. Okay. So this is the one. So the Shannon sampling theorem tells that if you take any band-limited function, this b by means any band-limited function of band-limited bandwidth phi can be reconstructed using this form. Okay. So that means if you are not terminal zero, just take any function of this form. Okay. F of x equals summation f of k sin pi x minus k by pi x minus k. So now look at this one. Okay. So what are the drawbacks of this things? First, what is the advantage? Why this problem, this term is very important? Because it converts the analog signal into digital signal. Because that means what is the meaning? If we know the function and only integer values, I can find the function f on the real numbers. Right? So that's why it's a powerful one. That means it converts the analog signal into digital signal. Okay, in fact, discrete signal, I am to say discrete signal, after that digital signal. Okay. So on this one I use red leave it. So first, what are the drawbacks of this equation number one? First thing is, if you want to reconstruct, you should look at this function. This you should know this kernel. Sin pi. This is okay, but look at this kernel. This kernel is something is not a good kernel. I think. That means what happened? This kernel is approximately equal to 1 by 2, and we know that the series summation 1 by k diverges. So due to that reason, the series always converges very slowly. Okay, so you can get the formula, but what happens? You may not get the solution very quickly. Suppose you are trying to write the algorithm based on that one, you will get the solution, but you don't know how many days it will take. Suppose the function is more complicated, or then sometimes you will get the solution, but sometimes it will take days to find the exact solution. Okay, so that's the first problem. Okay, the slow convergence. And another one, even if it is fine, but practically what happens? We won't take infinite summation. Because always we try to truncate it. Okay, infinite sum is not possible. Suppose you want to write code for based on computer, definitely you can't use the infinite sum. Okay, there is no for loop based on infinite sum. Okay, only always try to fix based on finite, right? So it is not possible. So always we try to truncate the summation, correct? Right? So that's the first drawback. So we always get the truncation. Is it okay? So next thing is, look, if you want to reconstruct the signal from the sample values, you should know present past sample as well as future samples. Because suppose I want to predict the value of the function at f of 2 by 3, I should know the values before values integer values less than 2 by 3, after 2 by 3 also. But practically what happens? It will always try to take only past sample. Future sample you can't decide immediately. It is very difficult. That means always we try to Here this formula is based on past and future samples. Okay, it is very difficult. Okay, because future sample is not possible always. Because if you want to predict means based on the past sample only you need to predict. You know, future sample will be then what's the meaning prediction? Okay, so that's why I'm telling that past samples only if you know in practically. So there are so many issues. Okay, we suppose what happens this sync function is due to sync function the series converges very slowly. Further, it depends upon infinite sum. Further, it depends upon all the past and future values. So there are so many issues. How to overcome this one? First thing is so just here see this one is a sync function sin pi x by pi x just you are translating by so instead of sync function try to choose some other nice function. For example, instead of b prime instead of sync function try to choose b prime Gaussian scaling function. Now you can read how I am writing now in the Euler theory or approximate theory you can see there are so many functions. For example, b prime is there, Gaussian scaling function there. For example, Gaussian function is a nice function because this compacting supported. So when you take compacting suppose there is a formula like that compacting supported, then automatically truncation will not happen. They here because of compare always you try to take only finite value, it will come. So there is you never get truncation error. So that will help. Again sometimes you need to choose the correct function such that it will give one. If you are going to find the value at the start, suppose you are trying to take compacting supported function at the same time, suppose you want to find the value at certain point x. It depends upon only past sample, then you are lucky. That means you are going to get operated simply the formula is simply prediction formula. Because you are trying to predict based on the previous past samples. Right? Okay. So now what are the important problems? So now what happened? Instead of choosing sync function, okay, you try to choose some other function, then try to get a similar type of sampling formula. Okay? Sampling formula. That is called Shannon type sampling formula. For safety derivation, because instead of taking sync function, you try to choose some arbitrary function, then you will get other spaces. For other spaces, you try to find the sampling formula. So that's a Shannon type sampling formula. So next problem. So in practically what happened? You never get the uniform sample. Suppose you never get uniform sample. Suppose you want to reconstruct an image, some blurred image you want to reconstruct based on some sampling formula. So remember that. Suppose the image is 100 years old. Suppose you are trying to take some photo, old photo. Now you want to reconstruct, you want to get the exact photo now based on the blurred photo. So now what happens? You can see that sometimes what happens, you see the photograph, maybe some places you will get a good image. There is a chance. Yeah, some places you may get a good image, some places too much blur. So you may not expect that the good image in the uniform places. You may not expect every time. Then always you try to get most of the time you try to get non-uniform. Mathematically okay, uniform okay, but practically you never get uniform non-uniform things. So you always try to get most of the time try to get non-uniform samples. Non-uniform that places only try to get the good information. Okay, so based on that information, how to do? So that's the main problem. So what happens? So some simple problem. Suppose it is the points are very close to the integer point. Still, it is possible to reconstruct. That is based on non-uniform sample, but at the same time, the non-uniform sample is very close to x n. Can we do it or not? That means what is the maximum value of this one? Okay, this one. How much if you disturb the integer sample, still you can do it. That's what characteristic. Okay. Next, maximum gap condition. Actually, there is a calculation for non-uniform sampling theory. So there is using Boolean lambda density. So Boolean lambda density, I am not finding Boolean lambda density is not easy. It is very difficult to compute. But instead of this one, a simple thing. What is the maximum gap between two consecutive samples to reconstruct the function from its on? Let me just suppose how much gap you need to choose. Suppose I can't take points randomly. I can't take samples randomly. Suppose I am trying to choose the samples in particular. For example, I am choosing f of x1. So f of x2, I am where I choose f of x, how much gap I need between x1 and x2. So that I can reconstruct. So what is the maximum gap between two consecutive samples? So this is the reason. Okay. So next one is the same problem. I am taking out for the classical one, the classical sampling. So instead of this one, you try to focus on the derivative sample. The derivative sampling is crucial in math, in real life. For example, suppose in air one system, for example.